before to start, I would like also to thank Matteo because he made my presentation much easier. So thank you, Matteo. So my presentation actually is really connected to the one of Matteo. We are in this presentation addressing how we can address data scarcity issue in robotics, especially for dynamic modeling of robotic systems. And to do that, basically what we would like to do is to leverage transformers. So we know that transformers are really good for NLP, and we would like to understand also if we can make use of their properties to generalize also system dynamics. So we would like to understand if we can make use of them as a meta model that is capable to include the generalizability capabilities for dynamical systems such as mass variation, control parameters variation, and so on and so forth, so that we can have a meta model that is capable to model a huge variety of robotic systems and therefore to adopt these for robot control also. So the idea is that if we think about standard identification problems, we basically have to collect a data set of input and output data, and then we need to create a model in order to estimate the behavior of the system based on the target input. And we would like to do, therefore, this, but using in-context learning. So if you do that, basically what we would like to implement is an algorithm that is taking as an input the input-output of our system. So for example, considering the robot, we would like to have as an input the control actions, and then we would like to have as an output the motion of the robot, the end effector motion, the joint motion. And then we would like to give as a context this as a context, basically. And then we would like to give as a task the complete control input, so the control torques, in order to predict the output for the rest part of the trajectory, so that we can use this prediction in order to estimate the behavior of the robot during the task execution, and therefore making use of this in order to implement, for example, an MPC. So we would like to estimate in advance what is going to be the behavior of the robot, and then making use of this estimation for control purposes. So basically, as we said, we can set up our problem in order to create a context, so an input-output pair of control actions and measured robot motion, and then we can provide also, and this will be the context for our transformer, and then we will provide also the full trajectory, the full control actions that we would like to execute. And finally, we would like to simulate the behavior of the robot while executing the target task. It has to be underlined that the context, in order to be effective, should be as small as possible, so that with a limited amount of data, we can estimate a bigger robot motion, so that we can actually make use of this estimation. And here is basically the robotic platform we are taking into consideration. It's a 7 degree of freedom robot. We are considering, as said, as input to the transformer the robot torques, so the control actions. And then we are considering as output of the system the Cartesian pose of the robot and effector plus the joint positions of the robot. Why to consider both? Because this is a redundant manipulator, and therefore we need, it is better to consider both the position and orientation of the end effector and the joint positions in order to fully describe the configuration of our system. And then, as said, the context should be as small as possible in order to provide us the possibility to estimate the behavior of the system with a limited amount of data, and therefore the percentage of the trajectory we would like to give as a context should be as small as possible. So to do that, in order to train our model, we need to collect data. And to collect data, first of all, we need to design the motion we would like to execute with our robot. So in this particular case, also based on the standard system identification procedure, we can, for example, generate multi-sinusoidal motions, chirp, signals, and so on, to have a rich trajectory in terms of frequency contact in order to excite our system and therefore to have some useful information to the model to model the dynamics of the system. Then we gather the data, we use the data to train the model, and finally we evaluate our system, our model, in order to understand if this model is capable to provide us useful information on the robot behavior. To do that, actually, we are using the Isaac GIM environment provided by NVIDIA. And this is really powerful because it's a GPU-based simulation environment capable to simulate thousands of robots in parallel. And this is extremely important in order to gather a lot of data in a reduced time. And indeed, doing this, we are capable to simulate many different trajectories, many different robotic dynamics with different parameters, and therefore we are able to collect a huge amount of data in order to train our model. And in such a way, if our simulation environment is reliable enough, we can actually produce a huge amount of data that might take a really long time in order to be produced with real robots. So in order to collect data, actually, we are considering two, let's say, random numerical input, multi-sinusoidal and chirp signals, in order to excite the system in a huge way. And then we are also considering some operational space control tasks, for example, executing circles or executing spiral tasks. So the main difference between these two families of signals are that the second one is basically general motion, random motion, while the first one is more related to the task we would like to execute. So it's a kind of specialized motion we would like then to test. And basically, we collect these data for thousands of robots, generalizing the parameters of these robotic systems, so varying the mass, the control gains, the friction in the joints, so that we can try to catch the different dynamics of these systems in order to create this meta model that should be capable online to detect, to model our specific system, and therefore then to provide us with an estimation of the specific robot behavior. And here we have a simulation of the chirp and multi-sinusoidal motions, just to give you an idea. And for each of the robot we are simulating in the Isaac GIM environment, we are generalizing, we are randomizing the parameters of these motions in order to collect the data in all the workspace and with the different parameters of the robotic system. And then here, instead, what we have is the spiral motion and the circle motion. And basically, the idea is the same. We can randomize the initial position, we can randomize the amplitude of the motion, we can randomize the robot parameters, and therefore we can collect a lot of data to be used in order to train our model. To evaluate the performance of, finally, our model after the training, we are considering these two indexes in order to understand how good our model is. And in particular, we are computing these indexes for each coordinate of the robot over the time. Then we are averaging these along the coordinates of the robot, and then finally across a batch of X robots in order to understand globally how this model is performing. And what we can also see is that after a few hours of data collection, actually it is already possible to have a quite good performance in modeling the dynamics of the robot, the generalized dynamics of the robot, especially for in-distribution data. So here what we have on the right side are in particular in red, is the error in the motion prediction for the Cartesian coordinates and for the joint coordinates. And usually this kind, and in particular what we can highlight is that this kind of error is quite small or small enough to be used into control algorithms in order to improve the performance of the robot during the motion execution. But what we would like also to understand is how this model is behaving with out-of-distribution data. And for example, here what we did was to apply a chirp signal with frequencies that are outside the ones that are used in order to generating the data. And in particular, if we are not moving so much far away from the data that we have, we can still achieve good performance in estimating the motion of our robot. And then, in order to improve again the performance of our system, what we can do is fine-tuning. So we can take the specific motion of the robot we would like to execute, and then we can add data. If we add new data, actually we can see that by adding data, we can improve the performance, and we can achieve a better accuracy of our motion, of our model, in order to predict the robot motion and make use of this in order to predict the robot behavior. And finally here is, we wanted to test also how training on a general chirp or multisinusoidal signal, how the model is then going to behave and to actually perform based on the execution of a custom specific motion that is, in this case, the spiral motion. So we have, in particular, that if we just try to apply the model as it is in a zero-shot way, basically the performance we are achieving are not so good. But if we then fine-tune, and we see this in the second column, the model on the specific spiral motion, then we can improve our performance, and we can actually achieve good enough performance for the purpose of our controller. And actually also this is going to provide a better performance than training only from scratch, 9 hours of training and gathering data, based only on the spiral motion. So this provides us as an insight that basically similarly to what we have in the standard system dynamics identification procedures, if we are able to gather data with a frequency content that is rich enough, actually we are able to generalize better the motion and to meta-modeling our system in a better way. So to conclude, for sure this kind of approach has some limitations. First of all, we collected for 16, 18 hours data in this GPU-based environment. That means we simulated really thousands and thousands of robots. So anyway, even if it is something that we can handle, we need to be actually to take this into account in order to balance our data set, to have enough data in order to create our model and to train our model and so on and so forth. And then as we saw also in this slide, the generalization is still something we need to take into account as an issue because actually, as we said, if we only train on the spiral motion, actually we are achieving a performance that is not as good as for the general training and then the fine-tuning on the spiral motion. And then finally, what we would like also to highlight is that we can make use of this kind of approach, as we said, in order to predict the motion of the robot to be implemented in a controller so that we can compensate for the errors that are going to arise during the task execution. We can also use this as in fault detection tasks. And as we said, we can also try to improve the transfer learning capabilities of this model in order to generalize better to new systems. So thank you a lot.